It's really a pleasure to be able to introduce Vladan Vuletic as our first speaker in this series. Vladan is the Lester Wolf Professor of Physics at MIT. He's a leader in a variety of topics in AMO physics, ranging from cavity QED, quantum metrology, trapped ions, nonlinear optics, and as we'll hear about today, also precision measurement. And so with that, Vladan, please go ahead.
Thank you very much. So welcome everybody. I'm speaking from the comfort of my attic here. And it's a little bit strange not to be able to see your faces and not be able to walk around, but bear with me, this is the first time I'm doing this. I'm starting this off with a quote from Arthur Shallow, as conveyed to me by my PhD advisor, Ted Hensch, who was Arthur Shallow's postdoc. And Arthur Shallow is famous for many interesting bon mots, and one of them was, to do successful research, you don't need to know everything, you just need to know one thing that is known. So that was probably meant as an encouraging thing for, say, new graduate students. But we have taken this maxim and, excuse me, I have to quickly restart sharing because my buttons don't work. Let's see. Yes. So we have chosen a topic where very little is known, which is the topic of dark matter. We virtually know almost nothing about dark matter. We don't know what kind of particle it is. We don't even know if it is a particle. If it is a particle, is it a single one? Is it many different ones? What is the mass of the particle? Many orders of magnitude are open. Nothing, almost nothing is known except that dark matter. So that brings me to the title of my talk. We are trying to do an experiment where we are measuring isotope shifts in the search for dark matter. The main contributing people here are listed here in dark. It's primarily Ian Counts, who has just graduated, and he was assisted by John Suk Hoor, who has done many of the calculation, as well as Diana Oda-Craig, a postdoc in our group. We have a lot of collaborators in this experiment that includes Won-Ho Jae and Hong-Ki Jin from the Seoul National University in South Korea, as well as Akio of Kawasaki, Julian Berengut, Geddes. And I would also like to thank my colleagues at MIT, Ronald, Richard, Jesse, and Phil Harris for interesting discussions. Sorry about that, it again stopped. Okay. So this is the outline of my talk. The principle is a search for a fifth force, essentially, through precision spectroscopy of optical transitions. I will tell you how that works and what theoretical proposal is based on. Then I will present our measurements, where we have 5 bosonic isotopes without nuclear spin that we have measured on 2 different narrow forbidden transitions. And as I will show you, we observe a nonlinearity in a so-called king plot at the 3.3 sigma level, which is a signature of either new physics or physics within the standard model or outside the standard model. And these are either nuclear effects that can cause such an observation or potentially a new boson. And I will discuss how we hope to distinguish these and how we hope to distinguish these in the future, both by improved measurements of higher accuracy and by measurements on more sensitive transitions. So this is really a fifth force search, as I said, made by a new boson that may or may not be the main constituent of dark matter. And it's the measurement of a boson of intermediate mass. How does this work? If you imagine that there's a new boson that we call phi, and that this new boson somehow couples both from neutrons and electrons, then it can be virtually exchanged between a neutron and electron. Here's the corresponding Feynman diagram. So basically, you can have the neutron emit virtually of this phi boson, and the electron absorb it, and vice versa. And we know generally that that gives rise to a so-called Yukawa potential. It's an 1/r potential that is cut off by an exponential length scale that is set by the Compton wavelength of the new boson, which goes as 1 over its mass. So basically, you get, if you have such a new particle, you get a new term besides your Coulomb potential in the interaction between neutrons and electrons. There could also be an interaction between protons and electrons due to this new boson, but we are not sensitive to it because we are looking at different isotopes with different neutron number. I would like to point out that these are not bosons that fly in through outer space somehow and hit our apparatus. These are actual bosons that are virtually created by as much as is allowed by Heisenberg uncertainty to mediate a new force. So another thing that Arthur Charlow said is never measure anything but frequency. Frequency measurements are by far the most accurate measurements that we have. And so again, following that maxim, we will measure transition frequency shift in atoms due to a Yukawa type potential. So the additional Yukawa potential that we would get for allowed, not yet excluded coupling strength. So of course, if this coupling was very, very strong, we would see it already in everyday life in normal spectroscopy. But if this coupling is weak, we may not have seen it. But the coupling strength that are reasonable, that are not excluded yet, would amount to kilohertz or less transition shifts for optical transitions. So unfortunately for the heavy ions, especially where these effects would be more pronounced, the absolute transition frequency cannot be calculated at this level. It's not possible to use atomic structure calculation, predict an absolute transition frequency, say in a terbium, what we use, at anywhere near that level. So there comes in a seminal idea by this group of people that includes Royo Zeri, Perez, and Sotek, and others. And there the idea was that to sidestep these absolute transition frequency calculations, we can instead compare experimentally the transition frequencies in species with different number of neutrons, so in different isotopes. We want to keep the same atom because we don't want to change the Coulomb potential. That would make a huge difference, of course, in the atomic transition frequencies. But if we just change the number of neutrons, then we are more sensitive in looking for a new force term. And so to rely purely on experimental data. So what does the isotope shift look like? This is one of the very few formulas that I will show you. So what is plotted on the left is the frequency shift between two different isotopes. I'm labeling the isotopes by Roman letters, J and I. You can think of J and I, for instance, as being the neutron number or the total mass of the particle. So I'm comparing two different isotopes, J and I, and I'm comparing them on a transition that I label with this Greek letter alpha. So this is the difference in transition frequency, in our case, in optical transition frequencies between two isotopes of the same atom, of the same element on some transition alpha. And it turns out that this isotope shift is by far dominated by two terms. The first term is called the field shift. It's a nuclear size effect. It's essentially the fact that if the nucleus was a point charge, you would have a 1/r potential. But because the nucleus has a finite size, at short distance, you don't no longer have this 1/r potential. And it turns out the leading order term goes as the RMS size of the nucleus squared. And in this case, because it's a difference between two transition frequency, it's the difference in RMS size squared between the isotopes J and I. And then in front, you have an electron wave function factor that basically just measures what is the electron density or the probability of the electron to find itself in this region where the Coulomb potential is modified. And the other large or relatively large term is one that goes with the mass difference. You can think of this so-called mass shift simply as the reduced mass of the electron. It's just the fact that because the nucleus has a finite mass, if you change the mass of the nucleus, you're changing the reduced mass of the electron. That's the so-called normal mass shift, but there are also correlation terms between the electrons in the kinetic energy. And so there's a second term that also scales in the same way with the mass of the nucleus. Again, this is a nuclear factor here, the mass difference, the inverse mass difference, times some factor that does not depend on the nucleus, but on the atomic transition. So what I've highlighted here in color is that each of these terms can be written as the product of a term that only depends on the nuclear properties, the size of the nucleus or the mass of the nucleus, and the term that only depends on the electron atomic structure properties, the electron wave function properties. Here, for instance, the probability to find the electron somewhere in here where the electron is and its correlations. So as I will show you in a moment, these two terms can be used to combine two different transitions to give a linear relationship between the isotope shift measured on one transition and the isotope shift measured on the other transition. Now, when we add the next order terms to it, there's two more terms of interest. One is a term that occurs within the standard model, and that is what you could term the second order field shift. That's a dominant term. So basically, to lowest order, you assume that the electron wave function does not change when you change the isotope. And so you just evaluate the changed nuclear radius together with the old electron wave function. But to second order, of course, you have the effect where because you change the isotope, the electron wave function changes, which in turn leads to a different energy shift from the size of the nucleus. This is the second order field shift. Again, can be written as a product of a term that depends only on nuclear properties, this delta R squared squared, and the term that only depends on the electronic properties. It turns out this term is dominated by the wave function near the nucleus, not surprisingly. And then comes another term, and that's the term that we are really interested in, and that would be a hypothetical term that could exist from this extra Yukawa potential that I've introduced. So that term in the isotope shift, in the frequency shift between isotopes, would scale proportional to lowest order, proportional to the mass difference between the two isotopes, so say the difference in neutron number. There would be a coupling term that is basically the strength of this Yukawa potential, the strength of the coupling of the neutron and the electron to the new boson, and then a term that depends on the electron wave function. And so this term really depends on the mass and therefore the range of the Yukawa potential. If the mass of the new particle is very light, then the Yukawa potential has a large range, and then you would be sensitive to an electron wave function far out. And if the new particle were very small, then the range would be short, and then you would be sensitive to the wave function close to the nucleus. And in general, these two terms will, as I will show you in a moment, give a nonlinear relationship. So how do you turn this into something measurable? You first divide by this every term by this reduced mass shift. So you get here, if you want, scaled frequency shift, which is this frequency shift between the two transitions divided by the mass difference. Here you get a scaled R squared divided by the mass difference, etc. And then you can use a second transition to eliminate this effect. Maybe I should say at this point that for us, for heavy atoms, this effect is on the order of gigahertz. This effect is on the order of maybe 10 megahertz. These are two linear terms. And then these terms here, for instance, this term can be estimated to be on the order of 1 kilohertz or less. So these are by far the dominant terms. Okay, so we divide by the reduced mass. We use a second transition to eliminate the size of the nucleus. And if we do that, we can write now the normalized frequency shift divided by mass on a transition beta between two isotopes J and I as being proportional to the normalized frequency shift on the transition alpha times some factor plus a constant. This constant comes from the mass shift, and then plus some term that comes from this nuclear second order field shift and potentially from the new boson. I should point out that both of these terms could have contributions that scale linearly with the normalized frequency shifts. So these would be invisible to us. They would be just reabsorbed into this term, but there could be or should be in general non-linear contributions. So what are we testing here? We are going to plot one modified transition frequencies the other versus the other modified or scaled transition frequency. And we expect the line from these two terms. And then we want to identify, say, the new boson term or potentially this term. And so we are checking whether things lie on a line. To check whether data lie on a line, you need at least 3 data points. And remember, each data point is a combination of 2 isotope shifts. So to plot 3 data points in this plot, you need at least 4 isotopes. Now it turns out that you need 4 spinless isotopes without nuclear spin, because if you have nuclear spin, you have hyperfine structure, and then things get a lot more complicated. And these corrections to these linear shifts, as far as we know today, we know already that they get much, much bigger, and we don't really know how to take out systems. So what do we need? We need atoms that have at least 4 isotopes without nuclear spin, that have narrow optical transitions, at least 2, and that can be laser cooled and trapped, so that a measurement precision on the order of kilohertz or maybe hertz can be realized. And that still leaves maybe a handful or so of known elements at the moment. Here, this is an example of such an isotope shift. This is from Benjamin Lev's work at Stanford, where they measured a new transition. And for instance, you see here beautifully that it follows this linearity. So this is the scaled isotope shift on one transition versus a scaled isotope shift on another transition. And you see this beautiful linear relationship. And when you zoom in, you see, well, maybe a little bit of deviation, but it's within the error. And this was a measurement with megahertz precision, as you can see by the error bars. And what we really need is a measurement with kilohertz and ultimately hertz precision. So if we had such a measurement, what would be what could we infer from it? This is from the seminal paper from Julian Berengut et al. That I mentioned before. The way these searches are usually plotted, the way they are plotted are, I'm trying to get my spotlight back, bear with me. Okay, the way these are plotted are usually you plot on the horizontal axis the mass of this new particle on a logarithmic axis. So this covers a range of maybe 7 orders of magnitude. And then on the vertical axis, also on a logarithmic scale, you plot the product of the coupling of this new hypothetical particle to the electron times the coupling to the neutron. It's because our interaction, our Yukawa potential, is proportional to both how strong this coupling is to the electron to the neutron. You see that these numbers are quite small. This is in some natural units, where basically one would be kind of the normal strength, the standard strength, and so we are talking here about many orders of magnitude below that. What is shown is this plot. What is shown is in this plot are in shaded the excluded regions. So this excluded regions at small masses below 100 eV or so, was eliminated or was excluded by fifth force measurements. The yellow shaded regions down here in this region are astrophysical observations. These are in general model dependent. So for instance, they depend on models of supernovae and so on, but these are using the models that are best known now to exclude these regions. These would be still worthwhile testing because, as I said before, they are model dependent. And then the blue shaded regions are excluded by laboratory experiments on Earth. So in particular, the dominant line here, the dominant limit, comes from G-2 measurements of the electron. The electron G-2 would also be sensitive to a hypothetical new particle, and so that measures the coupling to the electron. And then from neutron scattering experiments, because when you do neutron-neutron scattering, you would have an extra force from this new boson that would change measurements again. So from the known neutron scattering properties, you can get limits on the scattering on the coupling of the new boson to the neutron. And the product of these two enters these lines here. And maybe the thing to take away with the green line from this graph, the green line is ytterbium plus. And if you were to perform a measurement at 1 Hertz in ytterbium plus and you saw nothing, no nonlinearity, then you could exclude the coupling at this level. So you can see that at least compared to laboratory data, you could be at 1 Hertz 3 orders of magnitude better than existing limits with such a precision experiment. Maybe to give you an idea how the scales, for the scale of things, so the blue line here indicates Yukawa potential of a characteristic scale of 1 angstrom. So basically everything to the right of this line or to the right of this mass is a force range smaller than the size of the atom. So this is basically where the Yukawa potential range becomes smaller than the size of the atom. And the heavier the particle gets, the smaller this range becomes. And the red line over here indicates a force range that's smaller than the size of the nucleus. At this point, it becomes very hard or virtually impossible to distinguish the effect of a new boson from just the effects of the normal coupling, the kind of contact. So in this region here, the higher the mass, the sensitivity simply drops of this method. But you can see that, maybe to masses of 10 or 100 MeV or so, one can get still reasonable precision. I would like to point out another thing in this graph, and this is the so-called Atomkey anomaly. Maybe some of you have heard about it. It was somewhat in the news. So this is a measurement that was performed, a nuclear physics experiment that was performed. In this nuclear physics experiment, in this reference here from 2016, an excited beryllium nucleus was, 8 beryllium nucleus was created by bombarding a 7 lithium nucleus with protons to create 8 beryllium. 8 beryllium is essentially 2 helium nuclei together in an excited state. And they are in an excited state with a relatively high excitation energy for nuclear physics of about 17 to 20 MeV could be realized. And it was observed that this beryllium excited state, of course, decays. Most of the time it decays by gamma ray emission, but a small fraction of the time, about 1 in a million, it decays by emitting an electron-positron pair. What you would expect is that in the if it was decaying by gamma that is then converted into electron-positron pairs, then the electrons and positrons should come out basically in the forward direction. But was observed as a peak, a correlation between the positrons and the electrons at 140 degrees. And one standard or one possible explanation would be that some unknown particle that they call X particle was created that would then decay into electrons and positrons. And because this X particle flies off in a given direction, then there would be a correlation to finite angle. A second experiment was performed by the same group in the same apparatus, using now not beryllium, excited beryllium, but excited helium. And a similar effect was observed, except that the transition energy was a little bit different. Helium, it was 21 MeV, and the opening angle that was observed was 115 degrees instead of 140 degrees. And so a claim was made that both of these observations by the same group could be observed, could be explained by a single particle, this hypothetical X particle with an energy of about 17 MeV, corresponding mass, and that with a rest mass energy of 17 MeV, and with a certain coupling that was basically limited by other experiments. According to Quantum Magazine, this is the apparatus that the experiment was performed in, but this experiment has been criticized, that they used the same equipment for both experiments, and that when you look at the calibration curve for these experiments, this is the calibration curve down here, this is the observed data, and this is this bump in helium that was observed at near 110 degrees. It was also criticized, for instance, on the basis that this calibration in this region of these angles of interest is not very good. So people are now looking into repeating these experiments or performing other experiments, for instance, direct electron-positron collisions to create this particle that could shed light on this. But as I said before, if we could, for instance, perform a 1 Hertz ytterbium experiment, then we could in principle confirm or exclude the atomic key anomaly in this system. So maybe this would be a good time to stop briefly and see if there are any questions regarding this.
So we do have a couple of questions. The first one from early in your talk was, if it's a new boson, how do you know the potential will be Yukawa type potential?
So if it's a new boson, you know that in general it was a massless particle, for instance, a photon, it would give a 1/r potential. And then the reason why it becomes a Yukawa potential is basically because if you have a virtual emission of a particle, you can only violate Heisenberg uncertainty for a certain time. And so the Yukawa type potential, or this exponential cutoff, simply comes from the fact that the Heisenberg uncertainty, which says that you can violate a certain energy delta E delta T only for a certain time, that decreases as the mass increases, and therefore the range for which this particle can travel is limited. So this is a general feature of any such coupling that gives rise to Yukawa potentials.
Okay, we have another couple of questions just asked now. From Dima Budker, we have why only spinless isotopes, which I think you mentioned the hyperfine interaction, but maybe you can elaborate a bit more.
Yes, so it is known that when you have a hyperfine interaction, then it's known that it gives rise to residual deviations from the skin plots that are relatively large. One could hope, for instance, that if one measures all transition frequencies, that somehow the center of mass of the hyperfine, of an element with hyperfine transitions, lies on this line. To my knowledge, it is not well understood. So it's quite possible that it is actually possible to use elements or isotopes with nuclear spin, but it is not fully understood at this time. The spinless isotopes are certainly safe from this effect.
And then sort of related question that I suspect you're going to get to later in your talk, but if you observe nonlinearity, how do you attribute it to the new boson instead of to a second order field shift from the shape of the nucleus?
That's a very good question. I would like to defer. I will show you a diagram how in principle it can be distinguished, but later in the talk. Mm-hmm.
And then, so maybe we'll ask one more question, and then we can move on. Let you keep talking. But so I have a question, or well, there's a question that was asked. Can you explain what the cause of the resonances in the sensitivity plot are?
Oh, that's a very good question. So remember that we are basically measuring the effect on the difference. It's a frequency. It's a transition frequency. So it's a difference between some orbital in the ground state and some orbital in the excited state. And we are looking for energy shifts between these two levels. Now, for a certain range of the Yukawa potential, there will be generally often a point where the shift of the ground state is exactly the same as the shift of the excited state for that type of. So you have one wave function, you have a different wave function, but if you add an extra potential with a certain Yukawa, then you have at some point a cancellation. So basically these resonances here mean that for certain masses, for a given pair for a given transition, that is a given pair of levels, you simply have no sensitivity to the extra Yukawa potential because it would give an identical shift to both levels and therefore would not shift the transition frequency by much. But then if you use a different pair of states, then you can get this kind of an anti-resonance. It's a loss in sensitivity for the particular transition. Okay, maybe we continue on and there will be more opportunities to ask questions. Okay, so Arthur Schawlow also said always measure twice, once quick and dirty, and the second time the best you can. I want to alert everybody that this is still our quick and dirty measurement, although it was a little less dirty than we feared, and it was certainly not quite as quick as we hoped. But this is our first attempt at this. So we are going to perform a Ramsey spectroscopy on 5 spinless bosonic isotopes of ionic isotopes of ytterbium, which range from 168 ytterbium to 176 ytterbium. These are ytterbium ions. And we are going to perform it on 2 narrow quadrupole transitions, one at 435 nanometers to the D3 half state, and one at 411 nanometers to the D5 half state. The way we will perform this is we laser cool the ion and trap it. We can detect it by fluorescence on this cycling transition, on the strong cycling transition. Then after we know that an ion is there and laser cooled, we can try to drive a transition on one of these two levels, and we can check whether this transition has been successful by turning on back this laser light on the fluorescent detection and seeing whether the ion is still fluorescing, which means it stayed in the ground state, or whether the fluorescence has disappeared, which means it has made the transition to the D state. And then we can step through this frequency to get spectra. The frequency error of this quick and dirty measurement is at the moment around 300 Hertz. We certainly think that in the future this can be improved down to Hertz, and several other groups, for instance, the one of Royoseri for a different element, have shown this. So this is, for instance, what things look like. This is a Ramsey spectroscopy with shelving. So we are looking at the fluorescence after we have tried to drive this transition as a function of frequency, for instance. So we see Ramsey fringes here in the data that we then fit to extract the center of the line. So also, we are doing this experiment quick and dirty in the sense that we are not co-trapping 2 isotopes and trying to measure them at the same time. But what we do is we first take a say an hour or so measurements of one isotope. We fit a number of spectra. We get the center frequency from each of these spectrum as shown here. Then we switch to another isotope that we trap. We measure its resonance frequency, which is typically a few gigahertz away, maybe 2 gigahertz away. We switch back to the original isotope. We measure a little bit, then the second, and so on. And we average this for basically for any pair of isotopes. We have averaged this for a day. What you see here in the data is that there's a drift. And the drift is there simply because our flywheel, the thing that we use to lock the laser to, is an ultra low expansion cavity, ultra stable cavity. But for these experiments, it was not as good as, say, the best atomic clocks. So there was a relatively sizable linear drift of this cavity that we locked the laser to. So basically, we are comparing the atomic transition frequency or the ions transition frequency to the cavity. And so the cavity is linearly drifting. So we fit both with the same linear drift because this drift should be common mode. And then we compare the total fits. As you see, we have deviations on the order of a kilohertz. We think that these are primarily due to, one is offset drifts in our Pound River Hall lock to the ultra stable cavity. And the other thing is we may have used too much intensity to lock the cavity so that there may have been thermal effects that basically lead to cavity expansions. Nonetheless, we can have when we do average this 1 day measurement, we can have a frequency error in the relative transition frequency of about 300 Hertz. So if you make a king plot here of the 435 transition frequency versus the 411 transition frequency on the other axis, and this is divided by this reduced mass already, so this is already the scaled transition frequency, we see a nice linear dependence between these two. However, when we zoom in by a factor of 1,000,000, so basically we cut this axis between these 2 points, zoom in by a factor of 1,000,000, cut this axis between these 2 points, zoom in by a factor of 1,000,000, etc. So then basically we get to this kind of graph. So this red line is the previous linear fit from the previous graph. And these are for our 5 isotopes, our 4 isotope combinations. Here we are plotting always next neighbors. So we are comparing 176 to 174, 174 to 172, 172 to 170, and 170 to 168. The blue shaded regions are 1 sigma deviation. The typical distance from this line in frequency units is about 1 kilohertz. Most of these points deviate by about 2 sigma, between 1.5 and 2.5 sigma. And when we ask ourselves, what is the deviation of all these 4 points together from a linear dependency, then we find a 3.3 sigma effect at this current precision. This uncertainty is rather large. The reason is because these are normalized frequency differences. So not only our measured frequency enters, but also the mass uncertainty of the isotope. So 168, because it's a relatively rare isotope, I think less than 0.1% mass abundancy in natural samples. This isotope, its mass has not been measured very accurately. And so this error here is dominated by the mass error rather than by our own error, excuse me. But as you see, because this mass is common mode to both of these transition frequencies, it's mostly along this line and at the moment does not affect us. Nonetheless, Klaus Blaum has promised us, for instance, to reduce this mass uncertainty in 168 substantially, and also for the other points, so that we don't have to worry about mass uncertainties. These points here are limited by our current frequency uncertainty. So what we observe here is basically when we stretch this axis by a factor of 1,000,000, we see this deviation at a total level of 3.3 sigma. So how can we now, and this comes back to the question that somebody asked, how can we distinguish where this comes from? Is this the second order field shift, or is this a dark matter effect? So in this situation here, we have 4 data points, which means that when you fit a line to it, there will be a deviation when you fit the best linear fit to it. And the deviation can only take the form of 2 different types of deviation. One is this kind of zigzag deviation, where 1 point lies below, the other above, the third one below, and the 4th one above. And of course, it could have the opposite sign. And the other pattern that could be a nonlinearity is what you could call a curve deviation. So it could be that this point lies below, this above. Sorry, this point could also have lied above and this one below. So basically, there are two different nonlinearity measures in the system. One is how much zigzag deviation do we have, and the other one is how much curved deviation do we have. So the point is that because we know what the dark matter term should look like, we know what type of pattern we should see in the deviation if it comes from dark matter. We know what the ratio of essentially the zigzag deviation to the curved nonlinearity should be if the nonlinearity comes from an effect that scales with the neutron number. It's a known effect. And similarly, sorry, I miswrote this, mistyped this. This should have been the second order field shift. So this should have been a delta r squared squared. Because we can use our data also to extract delta r squared, we know in principle also what this term here looks like, which gives rise in general to some other different pattern. So basically these two give rise to different patterns of the nonlinearity, or potentially give rise to different patterns. So basically what we introduce now is this nonlinearity measure where we, if you think of this vertical deviation from the line as D174 for this combination, D172, D170, and D168, we can make two independent numbers. One is by doing D168 minus D170 plus D172 minus D174. So this zeta plus would be the zigzag nonlinearity. And if you put a minus sign here, then the zeta minus would measure this curved nonlinearity. So the point being here that we can characterize the nonlinearity further than by its sheer magnitude, not only how much does it deviate, but also in what way does it deviate. And just if we had even more isotopes, then you can even characterize it even better and restrict things even less. But at the moment we have 4 spinless isotopes. So if it works, for instance, to include spinful isotopes like Dima asked, then one would gain even more information from this. So this is our result. What I plot here is on the horizontal axis, the zigzag nonlinearity, and on the vertical axis, this curved type of nonlinearity. And then, as I said before, because we know what shape or how our dark matter should couple, how it should scale, we can predict a line along which any dark matter for a new boson should lie. This is this line, this blue line here. Basically, this blue line tells us that zigzag nonlinearity is stronger for dark matter than this other, the curved nonlinearity, and also it tells us what the particular pattern is. Zigzag is whether it lies above or below the line. So if the new boson had zero coupling, basically if the new boson doesn't exist, we would measure something right here. And if the new boson, if the effect that we see was purely from dark matter boson, we should observe something on this line that depends on coupling strength. In general, the stronger the coupling, the larger in effect we see in the zeta plus, so the larger the further out we lie. Similarly, if the effect comes from second order field shift, where we know how delta r squared, we can extract from our isotope shift data the size change in the nucleus, then we would lie along this green line here, like so. And that is the effect that would come from second order field shift. And the red region right here shows our 1 sigma measured effect. So we measure non-zero, about 3 sigma, and this is where we come to lie. So as you see, it could agree with the second order field shift, but also within 1 sigma or so, it can agree actually with a new boson. Or in general, the point could also lie here, so it could also be a combination of the two. So basically, the story is that if we improve our precision and measure something either here or somewhere here, we can improve our, we can start to distinguish between these two terms. The other way we can distinguish is the following. For second order field shift, we know that we lie along this line, but the second order field shift is basically this term that we know and we can measure. And then there's this atomic structure term that tells us how much the second order field shift matters for our particular transition. So in principle, we can, and we have some first results, we can make calculations to predict not only that we lie along this green line from the second order field shift, but also where the effect is. We have at the moment one preliminary calculation from Julian Berengut and his co-worker Amy Geddes, and their prediction at the moment, but very likely with a large systematic error, is that the second order field shift should be somewhere over here. We have also a very preliminary calculation from our own, from Jun Suk, our group, and his calculation is that the effect should be lying somewhere over here, although we have already found a systematic error, so we have to fix it. So what I want to say is, you know, if somebody from, especially somebody from the community, can give us help with the atomic structure calculations, and I don't know whether people like Mariana Safronova or Andrei Derevyanko, others are here, we could not only predict that what a second order field shift, on which line it should lie, but where it should be, and that would give us a lot more information to distinguish basically second order field shift from a potential new boson. So another way to plot our data is to say, well, we think we have evaluated other effects, and we think the second order field shift is the largest. So basically, what combination of new boson and second order field shifts are our results compatible with? So we plot along the horizontal axis the nonlinearity due to dark matter, or the coupling due to dark matter, 0 being no coupling to dark matter, no new boson. And on the vertical axis, we plot in some units the nonlinearity due to the second order field shift with some electronic structure factor that, as I said, in principle could be calculated. And our 1 sigma region corresponds to this. So it is consistent with no coupling to dark matter if the second order field shift takes on this value, or it's potentially also consistent with some coupling to dark matter. How can we improve this? Well, as I said before, we can improve the measurements. So if we improve our measurement, find our region, say, to be lying here, then we can infer both the nonlinearity due to second order field shift and to the dark matter coupling. That would be one way, by measurement. Or if we improve the calculation and know, for instance, that the value for the second order field shift were this one, then we would infer that we have to lie here, and therefore we would have a non-zero dark matter coupling in the future. So both on the experimental side and on the theoretical side, progress, I think, can in principle distinguish between these two effects. Where are we right now? If I come back to this kind of diagram where we plot the coupling strength, the product of the coupling strengths to the electron and to the neutron as a function of the mass of the particle, then and here's this ellipse before, then basically if we take this point, if we assume that we lie right here, so that, you know, that the second order field shift is negligibly small and all is dark matter coupling, then we would get this particular curve. The solid line is for the calculation by June in our group, Jun's curve, and the dot, these little crosses here, is a calculation of the same situation with a different method by our collaborators, Julian Berengut and Amy Geddes. So you see they agree relatively well, which gives us kind of confidence that apart from where these resonances exactly lie, they are very sensitive to the particular calculations. But apart from these anti-resonances where we have no sensitivity, we see that in this low mass region, we agree very, very well, and even the high mass region within a factor 2 or better or so, we agree with this. What this curve represents is, you should think of this as an upper bound for the dark matter coupling. So that's the dark matter coupling is this. But of course, the dark matter coupling could be weaker. So it could lie in principle below this line all the way to 0. As I said, we will learn more when we improve our measurements or when we get better calculations for the second order field shift. So we are about a factor 100 or so away from this Atomic anomaly at the moment. And we are within a factor 10 or 20 of these bounds on the G-2 of the electron and neutron. I should also say that these bounds are not completely firm. They are to a certain extent model dependent. And we have heard that, basically, depending on what model you assume for this dark matter boson, whether it's a spin 0 or spin 1 particle, for instance, or say if both exist at the same time or something like the whole family, this limit could move in a different direction. But in short, this is where we lie, and this is how we're pushing the frontier forward. So what can we do in the future? We can make a measurement on another transition. There's another very, very stable state in a terbium plus. This is for the expert, the so-called F level. This level is the level with the longest known lifetime of all known levels in any atom, I believe. Its lifetime is estimated to be 10 years. So if you placed an atom, an ion in this state, in vacuum, not perturbed, it will take 10 years to decay. It's because it's a triplet forbidden state. These other D levels have more lifetimes on the order of a second. We have found all the isotope shifts for these transitions, and we have actually measured them. We have completed the measurements, and the analysis is underway. Very, very preliminary is that we will, at our current understanding, confirm the nonlinearity and probably see an even larger nonlinearity on this one. We have to analyze this far more carefully. So the reason why this transition is interesting is, I didn't point this out in the beginning, when you compare to these states, you can only gain information about the dark matter coupling and also the nuclear effect to the extent that the levels are different. So in both cases, we start from the INS state, so that level doesn't contribute. And so only to the extent that the wave functions between the D3 half and the D5 half state are actually different, do you gain any information about dark states. That means that the given level of precision, the D state combination is not very sensitive to dark matter or nuclear physics. Whereas if you compare a D state to an F state that is very, very different, you get much more sensitivity. So roughly speaking, we get an order of magnitude more sensitivity to dark matter and to nuclear physics for the same experimental resolution and then for the D states. And we have measured the state with about the same or maybe a little bit lower resolution, but on the order of magnitude the same. So we expect better results from this transition. Something also in the future is if you want to push the transition sensitivity even further, when we compare D and F state, the S level is still common to both. And so we're just looking at about differences between D and F, and neither D or F states by themselves have a large electron density near the nucleus where the large mass matters. So if you instead compared, and you could do that, made the King plot with one transition from ytterbium plus and say the clock transition from neutral ytterbium, then these have different S states, which have very different electron densities near the nucleus. And so you would get, again, for the same precision, you would get a lot more sensitivity to dark matter. And this is something that we are at the moment evaluating theoretically and thinking of doing in the future. As I said before, more precise atomic structure calculations can help us distinguish between standard model effects and potentially new bosons, as well as precise measurements. And the thing that we really don't understand much about is, can one, for instance, calculate properties of the nucleus better to a level where it would actually help us to distinguish this at higher order effects in the nucleus that we might observe. And with this, I would like to thank you for your attention, and I will be happy to take more questions.
All right, thanks so much for the great talk, Vladan. So I think we have more assembled questions, and then as you were giving your talk, we decided to maybe give it a go where people can raise their hands and we'll call on people. But just because there were some people who were already following the rules, maybe we'll first select from the Q&A, Shimon, and then we can go from there.
Yeah, so what we thought is we could try to get people who would ask questions to actually speak. I think I can, for example, so Will Cairncross had a question. So Will, if you're ready with a microphone, I can say allowed to talk, and we can see if you can talk. Will, can you hear us and ask a question?
All right, so Will is now unmuted.
Okay, thanks for a nice talk, Vladan. Yeah, I wanted to ask, do nuclear shape contributions end at second order, or could there also be higher order contributions that have a different shape?
They don't end at second order. They are, there's in principle an infinite order. However, fortunately, these effects get weaker. So this is, we believe, the dominant term. Then there's a term that is the shape of the nucleus. There's a term that goes as delta R to the fourth difference. That term we believe is maybe a factor 10 to 100 smaller than this one. You get even higher order effects. The next effect after that is believed to be dominant, an effect that has never been observed, just like the shape effect has not really been measured, is the polarizability of the nucleus. So in the field of the electric field of the electron, the nucleus just ever so slightly deforms. Nuclear physicists would be very excited if this effect could be measured. We estimate that in our experiment, that effect should appear at maybe the 1 Hertz or below 1 Hertz level. So you're completely right. There's a whole scale of effects, but they get weaker and weaker. But as you push the precision, you start to see more of these. You start to see these extra effects that you need then to include. So basically, we think that the next effect beside the second order field shift is maybe a factor 100 or so smaller, and that would be a delta R to the 4 term, which is the shape change of the nucleus. Very good.
Thank you.
Okay, so we're getting a lot of questions. We're not going to be able to get to all of them, but we'll take as many as we can in the next sort of 7 minutes or so to end on time. We had one question via email that was, what about, so the plots that you showed, do they include both statistical and systematic uncertainty? It sort of looked only like statistical, but is systematic included as well?
So no, so the plots that we show are statistical. The error bars that we show are statistical errors. We have evaluated the systematic errors, and we think that they are all smaller than the statistical errors at our current level of understanding. So 300 Hertz is still a relatively large statistical error bar, and so we believe the systematic errors are smaller than this. Many things here really are common mode because you're doing everything the same, you're just switching out the isotope.
Okay, I think just
systematic
for the sake, just for the sake of time and because we have so many questions, I'll just ask the questions as opposed to trying to call on people. So we had a question: would it be possible to see this effect in the hydrogen atom? One only has 3 isotopes and they are not spinless, but the hyperfine structure and many more properties can be calculated with high accuracy.
That's a very good question. I believe that the effect is much smaller, but I haven't really ever evaluated it myself. I have tried to quickly estimate it. In principle, it should be observable in hydrogen, why not? I think that the effect in hydrogen is very, very small. And for hydrogen, what I relates also to the previous question. So there's also not only a second order field shift, but for instance, also a second order mass shift. It turns out that for the light particles, the mass shift is the dominant term. It's much larger than the field shift. And the mass shift is much, much less understood and modeled. So that would be, I think, a difficulty for doing it in hydrogen. But in principle, there should be a similar level shift there.
Okay, I'm going to try to say the names of the people who asked the questions now. Adam suggested it. So Martin Weitz asked, can you elaborate more on the assumed model for the increase of the nuclear RMS radius on the neutron number? Isn't this a critical issue?
This is a critical issue. So we actually use experimental data for this. So because we are measuring these transition frequencies, maybe in this graph here. So one way to measure these shifts is because we know that this is the dominant term. If you know the electron wave function F alpha, and we ever measured this shift accurately, you can actually get a value for this delta R squared with some systematic errors. And so basically isotope shift spectroscopy is used to calculate delta R squared. So we use both our own data, which agree with what other people have measured, also via electron scattering. And it turns out that the error, because this is a quadratic term, the error that we get, the systematic error that we get on the delta R squared is sufficiently small that for this quadratic term at the moment, it's not limiting us, but it's a very good question. So a delta R squared is not coming from modeling, it's actually coming from data.
Okay, Andrew JH asked, given that the electron G-2 sets limits for new bosons, can something be learned about the muon -2, G-2 discrepancy from isotope shift spectroscopy?
Very interesting. Yes, so I didn't put it in this graph. If the current deviation for the muon is confirmed, from the theoretical model, then it could be explained by a new particle that would lie in a band that kind of spreads right here. So beside this beryllium anomaly, if the muon is confirmed, there will be a preferred band here of couplings and masses that would explain simultaneously the muon anomaly. So yes, absolutely. At the level where we are already starting to get into the regime where one could, if we really observe a dark matter or don't observe a dark matter, where one could make inferences about what should be observed for the muon.
Marco Cetina, I hope I'm pronouncing that right, asked, could quantum logic on code-trapped isotopes be used to enhance sensitivity?
Definitely. Hi, Marco. It has actually been used. So if you co-trap atoms and then use quantum logic, then for instance, the group of Royozeri, and I'm sure some others have shown beautifully that you can push the precision not only to Hertz, but to sub-Hertz level. I believe that in strontium plus, they have measured an isotope shift between two different isotopes for precision below 100 millihertz or so. So basically another 4 or maybe 5 orders of magnitude are available if you co-trap two ions, measure at the same time, and use logic spectroscopy to measure the beat frequency between the two without being any more sensitive to the noise of the laser. So yes, absolutely.
Okay, Maxwell Ermi asked, would this new boson have a similar spatial distribution to that observed for dark matter, i.e. that it extends beyond the normal matter distribution in galaxies, or would the distribution of this boson mirror that of electron and neutron concentrations?
I really don't know the answer to that question. I guess it depends on the temperature of this. One could imagine that it's so weakly coupled that it only couples gravitationally and therefore does not thermalize or shrink with the other cloud. But I don't really know the answer. Also, people seem to favor at the moment not an explanation with one new dark boson, but the belief that there's maybe a whole dark family, a whole new kind of similar family to that exists in the standard model that is dark and only weakly coupled to our normal particles. So there may be more than one dark matter particle in these scenarios as well.
Okay, so we're running out of time, and there's been a few related questions that I'll try to combine into one. So is it possible that other species might provide better sensitivity for measuring these nonlinearities? And is there a good way of determining the best candidates? And then also, is it possible to potentially use molecules instead of atoms to enhance sensitivity?
Mm-hmm. These are all very good ideas and suggestions. If you look at this graph, you would conclude that ytterbium, being the heaviest, is the best at a given precision. As you see, for instance, ytterbium 1 Hertz is better than strontium 1 Hertz, is much better than calcium 1 Hertz, etc. However, one has also to look at the nonlinearities. And for these lighter elements, for instance, the nonlinearities are also predicted to be smaller. So in the end, if you want to suppress nonlinearities, at the moment, it's not clear which one is the best element to do. Certainly, if you thought it was dark matter, it would be great to perform it in several species and see whether the results are consistent with one another. And in principle, molecules could also, for narrow transitions, provide some information, because in molecules, you could measure many different levels, like, for instance, Tanya Zilewinski is planning to do. So I would say the answer, which element is the best to measure, is still open. We did this experiment because we had ytterbium plus in our lab, and so it was easier to do a quick and dirty experiment right now. But I think it's an open question, which one might be the best one to do it.
Okay, I think we'll stop there.
Yeah.
Yeah.
All I was going to say was, so next week we'll have Wasim Bakr, who will be speaking on transport and spectral properties of hot Fermi Hubbard systems. And also just a reminder to please sign up for the email list. Let's thank Vladan once more. Thank you.
Thanks a lot, Vladan. And thanks everyone for attending and for asking questions and participating and everything, and for your patience with us as we figure out the best way to do this.
Can you tell me how many people participated? I couldn't see it on my screen.
At the peak, we had something like 240 in the webinar and another 150 on YouTube.
Wow.
So we had
really? I didn't know there were so many on the YouTube. That's great.
We had about 400 people, plus or minus.
Great.
Yeah, so pretty good.
Awesome.
Thank you very much for inviting me to give this talk. It was
great, Vladan.
It was a great talk. Thanks so much. Really nice results and great talk. So we'll see you all next week on Friday. Thanks a lot.
Thanks. See you all.
See you.
Bye.
All right.